Okay. Hello again, everyone. I can see, people are slowly joining. But let's get going with our webinar. Once again, thank you very much for joining us. This presentation is a very quick walkthrough InSite seismic processor, especially focusing on trying to show some of the latest features in the new version 3.17 and how they apply to the processing of acoustic emission data. A bit of housekeeping. There is a chat. You should have a chat. You can leave your questions there and we'll go through them at the end of the presentation, just after the presentation. And we'll also open the floor for anyone that has any questions at the end. Okay. So, as I said, this webinar is titled Processing of Acoustic Emission Data, but it's basically an overview of InSite Seismic Processor, which is an integrated package for the management, the processing, analysis, and interpretation of seismic data at every scale. Acoustic emission is just one of the scales it works at, but basically it works on the principle that acoustic emissions in the lab are the equivalent to earthquakes on the Earth, and they have they share lots of similar processing techniques and similar approaches. This software has been developed over the last 20 years now, just over 20 years, basically through collaboration with different research institutes and through applications with our industrial partners. And well, we're going to use for this presentation the latest version, which was released last month in February 2021, version 3.17. Right. So, what's the workflow for processing of seismic data? And when I say seismic, it applies to microseismic or acoustic emission data. Well, the first step, as with any task, with any software, is setting up our project. Specific to this application is the extraction of data from the acoustic stream. Importing the data has been extracted if we are working on a trigger system. And the conditioning of our waveforms, they require some pre-processing. Basically, the removal of the DC, some filtering, some cleaning up of the signal so that it can be used for further interpretation. Once we have our signals, we need to classify them, as we might have noise, and there's always noise coming from our signals. Active surveys, very specific to the lab, and we will see where this arrow goes to in a minute. And the events, what we call the acoustic emission events, which are the ones that are giving us information on the fracture process. Of course, the next step is processing these events, this data, once it's been classified and when we have our defined events. Next step is processing them. This arrow indicates that active surveys are used also in this processing. They provide us with key information for optimizing this processing, such as the velocity model that we have in our sample. And finally, export and analysis of the data, extracting more than purely the location of our events, extracting more information from them that can help us to characterize the fracture process. And in the export, we can export our results, the results from our processing, or unprocessed data, waveform data that can be processed in a separate application. Well, first step is, of course, the setup of the project. And the setup of the project case of InSite and all seismic processing tools, indeed, first step is defining where our stations are. Stations, sensors, where our receivers in general locate and how they are. InSite allows basically any geometry for our monitoring array, and the geometry of the array can be determined by our sample, by the number of sensors that we have, or we can optimize them. We can do some preliminary study to optimize where we position them and the number of sensors that we use. But anyway, this is always the first step. Very important when working with acoustic emission is having our sensors calibrated, which is quite unusual, but if we have them calibrated, we can actually measure displacement, velocity, or acceleration, and from that obtain source parameters for our event. If not, we can still work on voltage, and we can still get some information, such as the location of our events and the definition of our fracture. So it's not that bad. Let's open InSite and have a look. And how we do that. So this is our first initial screen for InSite, which is blank at the moment because we don't have any events in it. And as I said, the first step will be setting up our array. This has already been done. In this case, I'm going to show how it's done. We can import directly our events from a predetermined file, a text file, where we have position and response properties of our array. So, yeah. Like that, or we can do that manually, add our sensors, our stations, one by one. And in this case, we have a dialog here where we can input the position of our tool, of our sensor. Our sensor can be uniaxial, or we can add more axes onto it, more channels onto it, in case we have a triaxial sensor, which is typical to have. And it is there, it is in each of our axes, in each of our channels, where we input the response of our sensor, because it's not common, but it can happen. The case where we have different sensitivities for different axes in one sensor. So it is here where we define the response of our instrument, such as the gain, sensitivity, and the frequency response. What would be taken from the transfer function of our sensor. So very simple. That's how we input our sensors. Now, each of these sensors will create a space in memory to store the waveform. That's why it's essential that we do this as our first step. And we can check that our sensors look reasonable. I also mentioned that we can, this is not necessary, but it's useful for us to insert an object that represents our sample, because we need a reference. It's always good to have a reference for our rock sample and how our sensors locate around our sample. So we can do that by one of these predefined shapes we have here. It can be cylinder, very normal shape, box, cuboid, ellipsoid, etc. What is new now in this version, in this latest version of InSite, is the capability to add other objects. objects that have been defined. They don't need to be. Oh, yeah, sorry. There's some interference. Okay. Hopefully it's clear now. Right. So I was saying what it's new in this version is the capability to import objects that have been drawn on a separate software, so we can have more complexity. And this is done through the import of STL files. STL files are stereolithography files, which are typical for 3D printing, and there's a big range of open source software that can be used to define this. So yeah, as I said, we can import using this new format any other objects that could serve as a reference. We need to define the coordinates. InSite has slight strange coordinates in that it's positive down as opposed to the normally it's positive up. But yeah, we can insert a rock sample of any shape. This will create the objects as triangulated objects, and these objects, they have also the ability to be used as filters. So we can call the event filter dialog and choose what is the object, in this case a rock, that we want to use as a filter. So they can be used as a special filter. So yeah, it can be any object, it can be rock. Just for amusement, I'm gonna show. In fact, you can even import some objects such as Baby Yoda. Whatever you can create on a 3D printing software, you can import it onto InSite. So once we have set up our project, the next step is, of course, bringing in data, bringing it in waveforms, which can be done in two ways. One is data harvesting if we are working with continuous streams, or we can import data that has been pre-triggered. If we're working with a trigger system of acquisition, we can import those events into InSite. So this is the interface in InSite for the direct import. And I think it's better if I show that in the software itself. So let's go back to our project. We go here to data visualizer, and yeah, this is the interface for import and manage data. And it's got a big list of formats that can be added, imported into InSite. One thing to mention is InSite and many other softwares do this is you import in one format, and then the software creates its own copy of the waveforms, and it's stored in a proprietary format. It's called the ESF. This is the one that I was selected there, but you can select any type of format. So you just point your data to an import directory wherever your data is stored. We will list the files that are stored in that import directory, and you just need to specify where you will store this data. It can be done in the same folder, but this is where the copy, the ESF files from InSite will be stored. And it's very simple. So just select and import. Would click on import. But I want to show what it's a bit more, probably more interesting in terms of working with, which is the leech. What will be? Yeah, I'm gonna open. So this, yeah, here we are. Will be the leaching. That is the open this project. Because this is the extraction of traces from a continuous stream. And this would be the interface. And in here we have options on how do we define our events. It can be simply defined as by a very simple amplitude threshold, that it's whenever our amplitude is exceeded, a certain amplitude is exceeded, a threshold that we can define here, then it will cut a section from the stream and save it as a waveform, as an event waveform. Or it can be a bit more complex, a high degree of complexity, which will be using a picking algorithm. That's more standard, which is a double window that does a search and compares relative amplitudes in a front and a back window in order to extract our trace, our event. And well, of course, this is that can be customized regarding what's the size of the waveform that we want to extract, and also how many sensors do we want to exceed this threshold in order to define an event. And that depends on the settings of our experiment, but the normal rule of thumb is half of the array at least should be exceeding this, and in order to define an event. So, well, I could just demonstrate this. Let's see. Works. Basically goes through traces. These are continuous traces in a sequence that would be the stream, and data is imported. In this case, because I selected automatically process during the import, it's also processing them. It's also picking and locating them at the same time. And you can see that, yeah, once it's done, it's finished. Now you can see that we have here a list of events. Right, which takes us to the next step. Let's go back to the presentation. Forgot to say, yeah, new in this version is that we have added the capability to stream and import data from other acquisition systems. Up to now, we were compatible with our own ASC system, but now it's compatible with the LSys and Mistras acquisition systems, which are, opens a whole new range of applications. So, next step will be, of course, the processing of the data, or in this case, pre-processing, waveform pre-processing. Nothing new in this version, but InSite has the capability to combine different types of filters for our data. And this is a standard step in dealing with acoustic emission data, because as a minimum, we need to remove the DC component from our traces in order to center our traces, our waveforms. But also we typically need to clean our data from either interferences from electrical equipment or noise that it's inherent to any experiment. We are breaking rock, so there's some friction in the plates, etc. that can induce some noise, typically of a very low frequency. So we typically need to apply a filter so that our arrivals are clear. And this would be the first step. If we go back to InSite, any of these applications. This is called here channel processing, and we can, as I said, combine different filters, band pass, low pass, etc., and we can combine it so that we can, for example, apply a band pass and take up a notch, take up a small notch that we see in our traces that are related to some noise. Also, we can go in more detail and apply different filters to different channels, to different sensors, and that's something that it's typical in our settings because some sensors are noisier than others, either because of their location. If we position sensors in the confining, the loading plates, for example, they will have different noise than sensors that are, for example, in the center of our trace, of our sample. But also, coupling can induce some noise or some can introduce some noise into the signal that might need a specific filtering. So there are options here to apply different filters for different sensors, different channels. And of course, we also have the option to define our own filter. And user-defined filter is just a text file, and that will let us define our filter. Right. So next step, I'm going to rush through some of these because they are very standard. So next step will be, of course, classifying our triggers. And that's done mostly visual. That's something that is judged by the user. But InSite will let you classify. So you pick one event and you can define what type of event it is. Is it a real event, shot, noise, or is it my own type of data? You can define events by being induced by plate noise, induced by hydraulic fracturing. You can introduce your own type of data, but it's important to take this step before we go into further processing, and we don't mix different types of events or surveys in our catalog. And we're going to the main step, which is the processing, and this is where we have introduced some changes. And well, this is just a cartoon, you probably all know, but this is the basis of our processing. How do we locate, how do we even detect an event, and how do we relate it to our fracture? Well, just because they propagate waves, they propagate the disturbance, stress drop is propagated as a wave. And the wave has different components. It has a compression, pressure wave, which is the P wave, and it has a normal or a shear wave that propagates with it. In our context of lab samples, we are typically working very close to the source, so there's no space so that we can clearly see the separation in between these two phases. So we normally just work with P waves. When we're working in the microseismic domain or earthquake domain, of course, we can see both phases, and being able to detect both help us in locating the events, because the separation in between them it's basically based on the velocity, that the different velocities that both components travel through the sample. But our first step is phase picking. And phase picking can be done manually, of course, or can be automated. And the automation, it's based on what we call a picking function. The picking function is just comparing what's happening at the front and the back windows, two different windows. And we assume that the front window will be the signal window, and that should have a significant higher amplitude than the back, which is the noise. And at the point where we exceed a threshold, comparing the amplitude of the front and the amplitude of the back, that will be the point where we have an arrival. But InSite will also let you introduce other variables in this peaking. So it's not only amplitude, you can introduce polarization, degree of polarization. You can introduce also the autocorrelation in our search, so that it's not purely based on a change in amplitude, but it's also based in linearity, polarization, or also just comparing it, just checking for a change in the pattern that we have in our trace when we have a signal as to when we have the when we are in the noise. But the main process, once we have picked our traces, is locating our events. And InSite has many different algorithms, and I'm going to show you some of them. Sorry, I have some questions. Yeah, I'm going to answer them. So is that when I say threshold amplitude on the window, you mean average amplitude in the window? Yes. Yeah, it's actually looking at the accumulated RMS amplitude. So it's taking the amplitude as a whole. So it's integrating the trace, basically, for the whole section that we take in our window. And that's what it's compared in between both windows. It's not maximum or average. It's accumulated amplitude. There was a previous question as well about calibration of the sensors in order to get source parameters. Well, that's not something that it's done automatically. It's something that needs to be done on an experiment when you are basically working with your sensors, calibrating your sensors. You will need to have a known source, for example, a vibration table, something like that. So you know what your source is, if it's displacement, velocity, or acceleration, and compare that with the response on your sensor. So that's the standard calibration. And then you know what will be the correspondence in between your voltage, the voltage that you're measuring, and the input vibration that you have in your sensor. Many sensors are calibrated, but it's not typical for piezoelectrics to have that. So back to our presentation. So yeah, location is typically based on comparing a theoretical pattern of either travel times or travel times combined with source vectors or propagated energy. Just comparing what would be the theoretical pattern, spatial pattern, with what we are observing in our data. And basically the point that minimizes the difference in between the theoretical and the observed, that would be the location. And there are many ways to both do the forward model, just calculate what would be the theoretical pattern, and the ways that we do the search for this minimum. And that's the difference in InSite. That's the different algorithms that we have in InSite. So for the forward modeling, at the moment, yeah, we have all these options. The standard homogeneous isotropic, which is fast, quick, and in many cases for rock samples is good enough for a first approach. We can introduce some degree of anisotropy in it, transverse isotropy. We can introduce layers, not so much in a sample. And at the end, we can also work with purely 3D models, because even if it's a small sample, a rock is never homogeneous, and there are known inhomogeneities. If we can model them, if we know where they are, we can work with these 3D models for creating what would be our forward model, the theoretical model. And then comes the inversion. How do we compare the theory with our observations? So InSite has these different inversion algorithms. the collapsing grid search, which is just purely a search over the space to compare. It goes through all the points in a grid, as it says, in the space to compare theoretical and observations. Then we have the simplex, which is a faster algorithm that doesn't go exhaustively through all the space. It basically guides the search. It tries to find one direction where our best match is found. It moves in that direction until it finds an adequate match. We can define what's adequate, basically, when we customize this algorithm. Geiger differs from the others in that it's not a search, it's directly solving the equations, solving the travel time equations. So it's a direct solving of the system of equations that we have. And then we have the source scan. It's also a slightly different algorithm. It is an exhaustive search. It's almost like a grid search, but it's got a migration in it. Basically, it tries to focus which point in a space will give us a best match for the energy that we are receiving in our traces. And in that sense, it's almost independent on the picking. All the others are based on what do we pick as travel times. Source scan doesn't rely on it so much on it because it searches, it just basically moves across the trace and tries to see which point in the space, in the search space, will give us an energy that matches the energy that we see maximized in our trace. So it's more looking into, it's almost like a combined picking and location algorithm. That's it. And it's good for basically bad data where faces are not easily identified, either automatically or manually. And this is just illustrating the search process for this grid search. And I'm going to show that in InSite because I want to show as well something that it's new in this version. Let's try to find what would be the... So, once we have imported our data, have a look at it. It's more useful. We have two ways of looking at them, as all the traces like this, stacked basically in depth, or independently as independent instruments. So, as we said before, the first step would be auto picking. Varies in this case. We might need to adjust a few of them. The manual pick didn't quite work in this one. So, yeah, we can adjust some of them. And yeah, here's where we select what will be the inversion that we're going to use, what is the model that we're going to use for the forward calculation. So the easiest will be the homogeneous isotropic. That's also quicker for this demonstration. Once we're happy with that, we just click on locate, and this is informing us on the whole process, on the search, how the search process works. And basically, it's telling us it's an iterative process, so it goes through all of them, all of the readings that we have for P wave arrivals, and it's telling us what's the difference in between what we have and the optimal solution, and identifies which of the readings is not matching the rest. Basically, it's not consistent with the rest, so it's considered an outlier. It drops it, does another pass without it, comes with what would be the best fit, and repeats the process until it goes on until all of the sensors are below a minimum, or sorry, a maximum residual that we allow, that we have allowed. In this case, the maximum RMS error that we allowed was 1 millisecond. So once they are all below that, it locates our event. It will give us also automatically the source parameters, and it has located. And we can go to the 3D visualizer and see, yeah, this is where our event locates. And of course, we can automate the process once we are happy with it. We can automate it. And it's pretty quick because we're working on a very simple velocity model. And here we get our locations, which are within our sample. Distribute. What is new in this version of InSite is the capability to use a 3D velocity model. A 3D velocity model, just for this demonstration, I've created a velocity model as a text file, a homogeneous velocity model, basically. I'm going to show you how it's defined. It's just basically a text file where you can introduce the center, the center of your boxes. So we have voxelized our space, our sample, our rock sample. In this case, we're working on a 1 by 1 centimeter cubes. We divide our sample in cubes of 1 by 1 centimeters. And we can define for each of those cubes what would be our VP velocity and our VS velocity. As I said, this is just homogeneous, just for the speed of the process, but this will let you introduce any complexities that we have in our sample, in our model. So it could be a void in the middle, or it could be, if we have a model of the distribution of velocities, we can, introduce them here. So by using that, I'm gonna go back to my example. We can, and in order, because this will be a very slow process. If we're working with a very complex model, the forward modeling for each individual event will take long. So the way we work with it is using this fast sweeping method builder, is that we're going to build a lookup table that will basically calculate what will be the propagation of our trace through this voxelized model. So we just look for this model. Oh, it's already there. So yeah, I've imported that and build it. It's telling me, this is the size. So basically what it does is do the process once, creates a file, a binary file that contains both what would be the travel times, source vector, etc. at each point of space, and then our search will just look for that. We just need to go back into that file and look and optimize our search through it. It doesn't have to perform again all the forward modeling for each simulation. So, the voxels. How do I define these voxels? Well, that's not done in this software. Something that you need to do either on an external modeling software, or as I did here manually. This is a very simple example. Close it. So I'm going to open it again. I just gridded the space. I did this meshing basically manually. But if you can use any meshing program, Rhino, for example, does it. So yeah, any software that allows you to voxelize or create a mesh in your sample and introduce the values, the different variables in it. So going back to InSite, let me go back to our location. Sorry, I've got too many open because I'm velocity. Yeah, here we are. So we finish that, and then we need to go back to our locator definition, and in this case, we're not going to work with a homogeneous model. We're going to work with a complex, and in this case, using the travel time grid method. Okay, and we go to project, and here we import this travel time data that we have, which is here. It's this Vel model, and we can reprocess. And in this case, it's quick because it's not doing the forward calculation for every event, for every single event. It's just going back to this file, this binary file that has been created, and compare. It's basically a lookup table method. Of course, because it's a small file in this case, because it's a homogeneous model, quite small. So we should get same results because in essence, we are using the same model, the same velocity. But yeah, this is a new functionality that we have introduced in InSite. It makes it easier to work with complex models. So once we have located our events, next step, of course, is calculating source parameters. And I'm going to skip the presentation because I want to show you something that it's new in InSite. And I think we don't want to run out of time. It's the way it displays mechanisms. So, as I said, once we have located our events, here we have a list of events that they all have been located. Go to the waveforms. Have a look like this. It's better. If we also pick the amplitudes, that can be automated. If we also know the amplitude of a first arrival, or what we consider to be the amplitude of our P wave, then we can calculate the source mechanism in two different ways. Just by inverting these first arrivals, would be the fault plane solution, or calculating the moment tensor. So if we click here, it's a quick process. It doesn't take long. It's not many variables in it. But basically, InSite decomposes. So the first calculation it does is calculating the moment tensor. It diagonalizes this moment tensor and calculates the deviatoric and isotropic components of it. So, yeah, the results are here for what would be our moment tensor. It also shows the deviatoric and isotropic components. These are the TK. So deviatoric is called T, isotropic is K. And they are used to display, if we go to here, this option, which is visualize the mechanism. I'll go back to what would be the, the other plot, because this would be the one that we typically know. It's the beach ball. The beach ball for this event in particular. Oh, good question. If we do need calibrated data to do the moment tensor analysis, yes, we do, because we need to know what that amplitude corresponds to. It wouldn't work simply on voltage. It needs to know whether it's displacement, velocity, or acceleration. But we can cheat. We can tell InSite that we know, because in fact, moment tensor analysis works with relative amplitudes. And if we tell it that our volts are in fact meters per second, the actual values of the seismic moment won't be correct. So what it's measured as a seismic moment won't be correct, but the components of the moment tensor will be correct. So the relative, so that will be the relationship in between the deviatoric and isotropic components will be correct. So one way to work with that, yeah, will be tricking InSite into belief that our sensors are calibrated. But yeah, so this would be the beach ball view. We see that we have two solutions here. One would be given by the pure fault plane solution. We select it only. It will be this one. It's just trying to separate as best as possible what will be the tension and pressure axis, areas in our focal sphere, or also the solution inverted from the moment tensor, which will be this one. Not always the same. It's a probabilistic calculation, of course, and it will never be exactly the same unless we have a very well defined data. What it's new in InSite is some changes into the TK plot. And the TK plot is useful when we're working with a large set of events, because here we can compare how our experiment or the events induced during our experiment have been changing from, let's say, double couple onto tension, or vice versa. Typically, it's the opposite. We start with tension, and we end up with having some double couple once we have a large fracture. So we have introduced some changes just to help, so we can introduce some interpretation labels. So basically, just telling you what TK is. It can be quite obscure sometimes what TK means. So, but it can also display, instead of just seeing the events as dots, displaying them as a density plane, because it will tell you sometimes, yeah, the eye doesn't interpret correctly where we have the majority of our events. So yeah, if we use this view, we can easily identify where the majority of our events position in the TK space. And also now it has the capability to use different color scales for our events. So if we go back to properties here, we can decide what are we going to plot as a color scale. Very useful is the time, but we might be interested also in scaling them by magnitude, just to identify what's the mechanism for our largest events, etc. So it's a display that has changed in this version of InSite, but I think it's a useful tool for interpreting, particularly a complete set of acoustic emissions. And I'm conscious of the time I'm taking, so I'm gonna skip some steps here, and basically this is how source parameters are calculated. This is just general theory. This is explaining what I have already explained about the source mechanism and moment tensor. But yeah, I wanted to show something that maybe not all of you are aware of. It was in the previous version of InSite, but it's quite recent, which is the capability to use velocity models that change with time. Because in the course of our experiment, we are inducing fractures, and the fractures will change. Of course, the characteristics of our material, especially in terms of how waves travel through it. And these changes in P and S wave, they have the reflection that can be interpreted in terms of rock properties. But the most important for us is velocity, because velocity will change where our events locate. It's not the same thing locating an event at the start of our experiment as at the end, where we might have a completely deformed rock. So for that, we can work with surveys. We perform if we have active surveys, we can use them to calculate a velocity model that can be anisotropic, and of course that can change in time. And I'm going to open a project in InSite just to demonstrate this. Okay, and it's this example I have here, which is back to our cylindrical sample, which is monitored through 12 piezoelectric sensors on the sides. But it also, all these sensors, they switch in between pulsing and receiving. So every few seconds or every few minutes, certain frequency, it performs a survey. So how can we use the information from this survey in InSite in order to obtain our velocity model? Well, I'm going to demonstrate it. We can use this chart tool and open. I'm going to show two different types of charts that are useful when we are carrying out a survey. It would be one is the survey stereonet chart that I'm going to ask it to refresh automatically to display the latest survey. And in it, we can, probably useful information will be what will be the P wave rather than travel time. I'm going to say, let's invert for travel time velocity. For P wave velocity from peak. Okay. And I'm going to add another chart, which is the velocity survey chart. And this one displays the velocity measured across different ray paths. So let's display what will be the P wave velocity. We can either do it calculated from the peak or from cross-correlating with a reference survey, the way. And we need to look at different ray paths, and we define them here. It's always useful, and I've got them, I'm cheating here. I'm going to go back to the 3D visualizer. I'm going to close this temporarily. Go back to the 3D visualizer, because we need to select, ray paths that could be representative of different areas in our sample, areas that could be subject to compression, that could be subject to, we know our fracture will develop or will grow in between them, etc. So we go here and select some representative ones. I will select one on the top, probably. One at the bottom will also be useful. One that crosses the whole sample in one direction, and another one that crosses in a different direction. Because in that way we can get an idea if some fabric is developing, some anisotropy is developing in our sample, and we can get a good idea of what's going on during the experiment. So if I go here, I'm going to add some ray paths that I already know could be interesting. So I'm going to add this. I think it was 6 to 7. 4 to 8. Right. So I'm going to display these two charts. I'm going to put them here. And they're blank. They both are blank initially because there are no surveys. So I'm going to simulate what will be happening in a real-time experiment. We'll be doing surveys every few minutes, every few seconds. So I'm going to simulate that we are performing surveys. So I'm going to import one survey at a time. You can see here is one survey has been processed. And have this chart has updated with this latest one. I'm going to import a new one. And this will be updated with the new one. And as we work, I forgot to do something which is properties here. I didn't ask it to refresh, so I will ask it to refresh every 10 seconds. So you can see very small, I'm trying to have everything in one window. You can see here changes. We have ray paths of relatively high velocity and ray paths of relatively low velocity. Some horizontal, some vertical. It depends on what part of the sample they are surveying. So if we keep adding more service, I think that was the last one I added. Add a new one. And this chart, yeah, they should be now updating. And there's some damage that it's developing on this ray path. These are going down in velocity. And if we go to the last one, we'll see a dramatic drop. Yeah, dramatic drop in velocities for all ray paths, because this is at the end of our test where, yeah, the sample has been completely damaged. So we can use this chart to actually create a time-dependent velocity model. And how would it work? It is saved, and it should be saved in this folder. And it is simply, very simply, a text file that will give us a VP, a VS. Well, VS hasn't been calculated, so yeah, there's no. And it gives us the time at where this velocity is valid. So it will be valid from this, well, date and time to the next one. So depending on when we carry out our surveys. And how is this determined? How is this VP? Well, in this case, we've chosen to use what would be the fastest velocity in all of the ray paths that we selected. Select the fastest, which it's the one that goes in this direction. It compares this one with the slowest, and it will assume that the slow direction is orthogonal to this one. So it will calculate what is the anisotropy factor, and it's a very simple anisotropy that it's defined. In this case, it's just what we call it an elliptical anisotropy that will assume that we have a fast direction and a slow direction, and in between it interpolates using an ellipse in between them, based on this anisotropy factor. So once we have this model, we go back to InSite, to the project. Yeah, here, for example, this one. Let's assume that we were at the same time in real time processing our events. But once we have that model, we can go to our locator properties. And instead of selecting one of these models, we can select a time-dependent transversely isotropic, which works with any location algorithm. It's just that the forward calculation will be performed using these velocity models that change with time. So not a new tool, but a tool that it's probably not very well known, and that was released in our past in version 3.16 last year. So anyway, sorry for the long time that it's taking this webinar is taken. We're going over the time that we stipulated initially. Hopefully you found it useful. Going back to my presentation, We will send you a copy of the presentations for everyone. So I just want to go to the last section here. Of course, you know us, but you can always contact us for any questions, general processing, InSite, whatever. I've got some questions here in the chat. Sorry, I didn't check. So how do you calibrate the survey sensor station corrections? Oh, yeah, good point. Well, that's not done in InSite. It's something that you do, again, separate. You can use, because you know where your pulsars locate, right? So you can use that survey position as an event, as a synthetic event, as a calibration shot. And because you know what will be the theoretical travel time from there to the rest of the sensors, you can actually measure any deviation from it and use that as a station correction, basically. So on a survey, you can treat each of the shots as a calibration shot that it's useful for its own calibration. And this is very particular to this setup in which, let's go and try to open this again. It's very specific to this setup in which each of the sensors poles are also pulsars at the same time. But if not, you can always have one pulsar that you know the location of, and you can use that to estimate any needed station corrections for the sensors. It's something I forgot to mention. You can, once you know station corrections, you can update that in your sensor properties. One of the properties for each of these sensors, in this case, is it's a P and S time correction in case it is needed. Hopefully this answer your question, John. If not, please let me know. All right. Well, yeah, yeah. So there's another question about regarding this station correction. Okay. Well, that's something we can discuss. I can give you a call if needed. We can discuss this in detail. What might be happening in the channels. But yeah, a survey will help. Definitely, a survey helps to identify this correction. We cannot do that with an event. It's too late when we are processing the events, basically. But we can use these surveys to correct for this. Yes, John, I'm taking note, and I will contact you, and we can discuss this. Okay, so if we have any other questions, and if not, once again, thank you very much for your time. Please feel free to contact us in any way through the website, direct email to us with any questions on general seismic processing, microseismic, acoustic emission, or specific to the use of InSite. Okay, thank you. I'm glad some of you found it helpful. And thank you for your time. And as is a rule at the moment, the best wish we can have for each other is stay safe, and hope to see you again next time. Bye.